Hi, welcome to my channel. I have been thinking about this following example for some time now. Among many attributes of the cube dissections, there are probably still some unexplored and perhaps some totally new problems. For example, we can have two polyhedras of the same volume and surface area yet look completely differently. Like in this instance, we have a cube which is surrounded by quadro-oblique octahedrons on opposite ends, but now I can place this half octahedron in here. Well, this actually is forming now a rhombic dodecahedron, but that's not what I want to show. I just want to show that this shape is obviously totally different than the shape shown previously, like this one. Yet they have the same surface and the same volume. Let me show some other example. And there is infinite number of examples like these, but I just want to show this for clarity so everybody who sees this understand where I am going with this. Here I want to show, for example, a unit of the truss. I'm going to remove these regular tetrahedrons from our cube octahedron, just like that. I'm going to remove these. These are solid kites. Anyway. Here we have a regular octahedron, and we're going to place tetrahedrons like such. And this is an octet unit truss. That's how this is known, or face-centered cubic lattice, or isotropic vector matrix. That doesn't matter. But what I want to show here, that this solid has 3, 6, 7, 8, 9, 10, 11, 12 equilateral triangles. Now I can place this in here, and we have a regular rhombic hexahedron, also 12 equilateral triangles, same volume, same surface, totally different solid. Here, let me show this. Now I split the octahedron in half, and I'm just gonna fuse them on the edges, just like that. And then I'm gonna fill these voids with regular tetrahedron, like that. And we have again a rhombic cube, squashed cube. All the edges are of same length, but now the top and the bottom is square. This is also an octet truss or isotropic vector matrix, because these are space fillers. If I fill space with these all around, I put other octahedron here, and then it's going to alternate with tetrahedron. It's the same and one and the same thing. But now I want to flip this in here, and we said we had 12. We said we had, okay, what we had? We had 2 squares and 8 equilateral triangles. Now if I flip it like this, we have also 2 squares and 1, 2, 3, 4, 5, 6, 7, 8 equilateral triangles. This is actually a part of a cube octahedron, little bit more than a 1/3 of the cube octahedron. But as you see, 2 different solids, exactly same volumes and same surface area. Now let me go back to the cube octahedron. The cube octahedron here. Well, almost. I have to remove these. We're going to put back our regular tetrahedrons. We're going to pop them back. Nice and easy. You can do this with any other magnets. This is so wonderful. I can join anything to anything. But anyway, we have a cube octahedron. It's a very familiar solid to many of us. Now I'm going to split this one on a hexagonal plane like that. It's not always easy, of course, because these magnets are kind of strong. Alright, there we go. So we have a cube octahedron. This is how it looks from a top view. You see it. Now we're going to fuse them, but I'm going to, from a cube octahedron which we had originally, I'm just going to rotate 60 degrees, where now we have neighboring squares next to one another, as you see. And again, we have the same solid like the cube octahedron, except we rotated it, has the same surface, same volume, but obviously it is a different solid. But the question is, can we have two tetrahedrons of the same surface and volume yet be completely different? Well, answer appears to be no. Even though this has been approached, I'm not sure if or when definitive proof exists. But for this very reason I have decided that the left and right double corner, which are these two modules, so this is left and this is right, are actually the same, one and the same module. If I would classify these two blocks as different modules because of their left-right hand orientation, it would mean that indeed there are two tetrahedrons of the same surface volume yet appear to be completely different. But as we see, it is not true, because all the edge lengths, all the angles, all the surface, all the volume, everything is exactly the same. For example, what I want to show also, excuse me, for example, if we have a two quarter oblate octahedron, this, as you see, it's an oblate octahedron. This is a half of it. Well, we split it in half, so it's a quarter oblate octahedrons. And now I can fuse them like this and have a left-oriented module. The reason I call this one left, because the right degree angle is on the left side where they appear in a cube, because these blocks build cubes, small cube, and that's how they appear. So this is a left-handed, but watch this. And I already have demonstrated this on other videos. I do this, and voila. Now I have the same module, which was left just a second ago. Now it's a right-oriented double corner. So what this tells to me, that one can be reassembled into the other, or each on its own has the quality of the other. If I would classify the left or right oriented module as two different modules, they could not share all the properties. There is nothing in their makeup that is not shared.